Okay, so this video is basically an introduction video to derivatives. Now, I have already done derivatives before, so this is kind of like an introduction to derivatives, and like it's kind of like an update. You can call it like that way. Everything needs an update, so why not these things, right? So those videos were um, quite old, so I was thinking maybe I should update it, right? And that's it. And then like I've changed the language as well, because like um, just to broaden the spectrum actually, right? So anyway, let's just get started with this. So this is derivatives. What is derivatives? Derivatives basically means is the rate of change, right? It's the rate of change. Now, when we are talking about it in terms of mathematics, then obviously what we are doing is we are talking about a function, right? So function, let's say you are talking about a function f of x, which is being made by a variable which is x, right? So what you're planning to do is to know what is the change of these things. For that matter, what you're trying to know is what is the change, what is the rate of change of this function if you make a change in the variable which is making up the function, right? So you can think of derivative in this way, that it is the rate of change of a function with respect to the variable which makes the function, right? Something like that, right? It's not like the ideal definition obviously, but it's just it just gets you there, and it just it just makes things easier, so that's why I just gave it like anyway. You can think of it in that way. F of x is the function, so what we are trying to find is basically, let's say first, if this rate of change is the first, we need to understand what is the change, right? So if it's the function that you're studying with f of x, then if it changes, then it becomes, let's say, f of x plus h, right? Like it was f of x, now it became f of x plus h. Why did it become f of x plus h? Because the variable which is making up the function, that variable x changed to x plus h, right? So you can understand it in different ways, right? In your daily life you can think about it, right? So let's say there is a function of your expense, right? In a monthly expense of or yearly expense. So if one of the variables which is in the expense which you need to calculate as an expense, if that changes, let's say the price of milk increased, right? Or maybe something else, like the price like that you pay for daily commute, that changes, right? The transportation cost, if it increases or something, then the total overall cost changes, right? So this is what it calculates. So what is at what rate this is changing, right? You do understand? So that if you want to know, so that for the rate of change of this function, what we are going to do is, first you need to consider the change in the function, that we write f of x. The change of the function can be written like this: delta f of x, right? That is the change of the function. And the change of the variable which is creating the function for the first place, that would be delta of x, right? There is a change in the variable, right, which is creating the function, right? So this is the function itself which is being made by this, which is the variable. So if I divide these two, take a ratio of these two, then that gives you the rate of change of the function, right? This is the rate of change of the function. So is this the thing that we are trying to talk about? Is it? It is, but not quite, right? It's you just have to go a little further than this. So think about it. If I just want to know what this is, then we can just directly put all this. So the function became this, and earlier it was this. So that's for delta f of x would become something like this. No, f of x plus h minus of f of x, right? Because it was this and it became this, so the delta of f of x is this, right? That is a change in the function, right? So divided by the change in the variable, so that would be equals to, the variable became x plus h, right? And earlier it was x, so that is where it is. So if you do the math, then it becomes f of x plus h minus of f of x, divided by x gets cancelled, so you're left with h, right? That's what it is, right? So that is the rate of change of the function, right? Now you will keep this only, this is what the thing, but if you just put another small thing, right, if you implement this, that limit h tending to 0, right, and this becomes f of x plus h minus f of x divided by h, the same thing that I have written here, that is the rate of change of the function. If I just write this and implement this limit here, right, then this can be called the derivative of the function, right? If we can write it like this, f prime of x maybe, or maybe d dx of f of x, something like that, or for that matter you can also write it like dy dx if you consider the function f of x as y, right? So that is what it is. So all these things are talking about the same thing, right, that we are considering the rate of change of the function with respect to the variable which is creating the function. For a change of the variable, and that change has to be as small as possible, right? For a smallest change of the variable that is creating the function, right, how much the function is changing, at what rate the function is changing, that is what we are trying to understand in this chapter, right? The derivatives, right? So that is the whole thing, right? So this is the formula we are going to use for some time, right? So this is what you call the, like the first principles. This is how it actually gets introduced to us. So this is what it is. This is the first principle. We consider this the first principle of derivative, right? Principle. So that's what it is. Understood, right? So now if we try and do an example of how this thing actually works, let's say you have a function, for that matter, let's say you have a function like f of x is equals to x square, right? So now if I think of a change of this function, so x became like x plus h. So if this happens, then f of x becomes f of x plus h, right? So you can think of it like, so what is the delta of f of x? So that is what the function became, that is f of x plus h minus of f of x, right? So that is a change in the function. Like the function became this, and earlier the function was this, right? So the change in this, and then if you want to consider what is the change in the variable which is creating the function, then the change in that is x plus h, that is what the variable finally got to, and initially it was x, so this is technically just h, right? So now if I do this, right, do the math, then it becomes what, right? So no, we can do this also, like straight away, right? So if I put the value, this becomes what, x plus h whole square, because like the variable which is creating the function, that become x plus h. So overall the function is x plus h whole square minus of x square, that is the function how it was. So if I put the values in this, then what are we going to get? So limit h tending to 0. Why is it that h tending to 0? That is the change, right? There is a change in the variable which is creating the function, right? So we are considering this for the smallest change, so that is why we have put this limit h tending to 0, while the change is going as close as it can to 0. So now this would be x plus h whole square minus of x square divided by h, right? So if I put all the values, then this is what it becomes, right? So now if you think of it, then limit h tending to 0, this becomes x square plus 2xh plus h square minus of x square whole divided by h, right? So now you can cancel all these things out, this and this gets cancelled. So eventually what you're left with is limit h tending to 0, then 2 of xh divided by, if I distribute it, right, then that becomes 2x, right? And then we can say that limit, right, h tending to 0, So this becomes h, right? Because h square by h is h, right? So now if you say like what if you want to take the limit, then here there is no place where you can put the value, right, of h tending to 0, but here there is. So this becomes what? This becomes 0 itself, it goes away. So eventually you are left with 2x. If you take the limit, then eventually you're left with 2x. So that's the value of the derivative. So what we're trying to say is that if prime of x, the first derivative of x, if f of x is x square, then the first derivative of x square is 2x, right? So you can think of it like this. So if you consider like y equals to x square, right, then dy dx, right, that is the first derivative, that is 2x, right? Like that you can go through the whole operation for all the things, right? All the mathematical function, you can go on to do all the operations with first principle. But you can understand, you can see that this is a hectic process, this is a complicated process, and it's like there's a lot of places where you could go wrong actually, right? Because you got to do a lot of things, right? So people have actually done this, and they have come up with some formulas and some shortcuts, right? So that is what I'm planning to give you now. So if we just consider some f of x, and let's say if I write what is the derivative, first derivative of that f of x, then this is how it goes. So actually people have actually done it, you can also do it, right? And you have to use different, different tricks and turns of different like different mathematics actually, right? Maybe some tricks of limits, maybe some tricks of trigonometry, who knows, like there can be like there can be a set of tricks that you can use to come up with this. So that is why I was saying like this gets difficult actually. If you do it with first principle, it gets difficult. So in your exams they might ask you to do like one or two easy things by first principle, but if it gets complicated, then it gets really tedious, right, to do like derivatives with first principle. So people have actually done it earlier, and they have come up with this formulas, right? So that is what I'm going to write here. So let's say first is, let's say you have something like x to the power n as a function, then the derivative would be n into x to the power n minus 1. Understand this. So the power of x was n, right? So x, the exponent is n. So now if you do the differentiation, this n becomes n, kind of becomes the coefficient, and the exponent gets like decreased by 1, right? Makes sense, right? So the exponent is n, now it becomes the coefficient, and the exponent itself decreases by 1, right? That is what it is. So that is what actually happened in earlier example. Think about it. We had x square, and now this square, this exponent became the coefficient, right? And then the exponent decreases by 1. So then it becomes 2x to the power 1, and so we can choose not to write the 1, because we understand that if the exponent is just 1, then it can be written, or it just, if you don't, even if you don't write it, then it's okay, right? So that is what it is. So 2 to the power x, we can 2 into x we can write like that. So that is what it is. This is coming from this formula only, right? So that is one. Then we can think of it, let's say there is another function, this log of x. So this becomes 1 by x, right? And then if you have like e to the power x, then this becomes e to the power x. And actually before this I should have written this thing, a to the power x. So this becomes a to the power x log of a, right? So that is what it is. So what is this? This is like there is a constant number, and on top of it there is a variable as a exponent, right? Constant number, and on top of it there is a variable which is an exponent, right? So now if you are trying to take the derivative of this, then this becomes like this, right? So the whole thing remains the same, right? But you need to multiply it with a log a. So for e to the power x, if you think the same, right? So e is a constant number, and top of it is a variable e to the power x, variable x, right? So this should be like e to the power x log of e. So log of e is basically 1, so it becomes eventually e to the power x only, right? So while when we are doing calculus, mostly logs base has been taken, logs base is taken as e, not 10, right? So there are two kinds, right? Log, and in your calculators you can find log or ln. So mostly we are working with ln, natural log, where the base is e, right? So for log the base is 10, so for this the log the base is just e. So that is what we are doing, right? So next is, let's say if we consider trigonometric functions. So then let's say there is sine of x, so this becomes cos of x. If you have cos of x, then this becomes minus sine of x, right? Then if you have tan of x, then this becomes sec square x, right? Then if you have sec of x, then it becomes sec x tan x, right? And then if you have what else, sec cosec x maybe, right? Cosec x, then it becomes cot x cosec x, right? But you have to have a minus right in front of it. And then if you have cot x, if you have cot x, so then it has to be cosec square x, right? So you have to have a minus right in front of it. So this is kind of like the formulas that you might need to get differentiations, right? For that matter, derivatives actually, right? If you want to do it, so this is the formulas that you might need. So this, and all these things actually comes from the first principle. So now people have done it for us, so that we can solve, like even more complicated functions, like even more complicated mathematics with the help of this. So the first part they have done it for us and then you are expected to do better and more complicated and harder problems, right? Solve harder problems with this, right? Because like earlier people have figured these things out, and they're expecting you to figure out other things, right? So that is what it is. Now having said that, there is some other things that we need to consider in this chapter. So in derivatives, so there are certain kind of ways by which you can actually do the calculations, right? So in differentiation there are two kinds, maybe actually three kinds, like there is rules, right? So there is one rule which is called the product rule, right? So there is just product rule, right? So let's say you have a function which is multiplied. Both of the functions are multiplied, and both of these functions are functions of x. Let's say you have a function which is like f of x, right, which is the product of two functions. Let's say g of x and h of x, right, like that, right? So both of these functions are functions of x itself, and they are combining themselves as a product, and it becomes another function f of x, which is obviously a function of x itself. So you get, I believe you're understanding this, right? So now if you want to do this thing derivative of these functions, then this becomes, you have to do the differentiation of the first function, so that becomes g prime of x, and then h of x just remains as it is, and then you have to do the differentiation of h of x, so h prime of x, and then the first function just remains as it is. This is what you call the product rule. There is another rule which is called the quotient rule, right? This rule is just the extension of product rule basically. So if you have, let's say, f of x in the form of, let's say, g of x and h of x, right, then if you do the differentiation, then it becomes, if you have to do the differentiation of the numerator first, so g prime of x, and then the denominator just gets multiplied as it is, and then you put a minus sign, then you write h prime of x, the differentiation of the denominator, and then you multiply the numerator as it is, right? And then you divide the whole thing with the numerator square, right? Numerator square. So this is basically an extension of product rule only. I mean, you can just think of it that f of x is equals to g of x and then h of x to the power minus 1, right? If you write this thing like this and then do the same procedure of product rule, in this you'll find this only, right? But if you try to do it now, then you might stumble a bit, because there is another rule which has to get implemented in it, right, which I'm coming to. So there is another rule that is called the chain rule, right? So the chain rule considers this particular kind of function, which we call the function of function, like the composite functions, right? So let's say there is two functions which is inside another function, or you can say like two functions which is inside one another. You can think about it, right, like that. Let's say there is f of x, right? There is f of x, and then there is g of x. Then there is one function which is called f of g, right? So here the function will be written as f of g of x, right? So f of x becomes f of g of x. I mean, like wherever the variable which is creating the function was to be, right, there we are putting the g of x itself, right? So there has to be, like, let's say, I'm just giving you an example. Let's say the function is f of x is equals to x square minus 2, something like that, right? And let's say the g of x function is like, let's say, I don't know, maybe tan of x, right? So now what I'm planning to do is, wherever there is x, right, which is creating the function f of x, so I'm going to put, instead of x, I'm going to put this tan of x, right? So if I write f of g, which is f of g of x, right? So that is tan of x whole square, right, minus 2. So what I'm trying, what I did is, wherever there is this variable which is creating this function, I have put tan x in that place, right? So then this becomes this, right? So that is what you call f of g, right? And then there is another thing which is called the g of f, right? G of f of x, right? So that is g of f, right? So this becomes, then think about it, this is tan of x, where there is x, we'll put this, right? So tan of, in place of x we'll put this, so this x square minus 2, like that, right? So these are called composite functions. One function is inside another function. If you have to do, the differentiation of this kind of function, then this becomes, let's say, if you want to do the derivatives like d dx of f of g of x, if you want to do this, then what it becomes is, first you do the derivative of the outside function, so this becomes f prime of g of x, right? And then you go inside, you just keep on getting inside, right? So you multiply the whole thing with g prime of x, right? And then if you had something inside of it, then you just keep on going and keep on multiplying the whole thing, right, with one another, right? So let's say if I give you an example, let's say you have, log of sine x, for that matter, alright? So log is a function, and then inside of it there is sine of x. So if you have to do the differentiation of this thing, so this becomes, the differentiation becomes, first you do the differentiation of the outside thing. So we know log's differentiation is 1 by, it happens to be, so this becomes 1 by sine of x, right? Then you go inside of it and make it a product. So sine of x's differentiation is cos of x, like that. You just keep on going. So now you don't have to go on any further. So this becomes cos x by sine x, which becomes cot x, right? So that is how you need to do it, right? So these are some of the tools that you need to introduce some of the tools that you need to use in differentiation, right? And you can keep going with this, right? And so this is kind of the whole thing of differentiation that you need to do. Like there are many other things, like intricate things, which is which delves uh, and it just goes deeper, for that matter, right? But overall you have to do these things, right? And then now if you practice a lot of problems, whether it is from first principle or normal differentiation, there are other things, explicit differentiation, implicit differentiation, there are other things, but everything is just revolving around these concepts, right? And then there are other things. So we'll just keep moving with this, right? We'll do a bunch of problems and you'll get to understand what I'm trying to talk about, and then we'll go eventually we'll go on to this other parts of differentiation where it gets a bit complicated, right? It just, but they're using the same things, but like afterwards you'd be using better tricks actually, but eventually you are just doing this thing only, but it can get complicated. That is what it is. So for complicated things we need to use better tricks, so that is what it is.